Hello and welcome to Chemistry the Right Way with me, Mr. Wright. On today's 10-minute tutorial, we're going to be talking about the gold foil experiment, which is actually a series of experiments famously attributed to Ernest Rutherford, who was actually supervising the two people who carried out much of the experimentation, which are two scientists called Geiger and Marsden, obviously very famous in their own right as well. It was performed at the University of Manchester over a series of years at the sort of beginning of the last century, sort of like 1905 to 1914, 1915, in that area. And the reason it's so important to our understanding of chemistry, and you know, we talk about the gold foil experiment, it's really a series, but we talk about the gold foil experiments conceptual all the way through to advanced chemistry classes, is because it lays out what we have today for our ideas of modern atomic structure. So here we go. So gold foil experiment resulted in, or came about because of work that was done previously by a physicist called J.J. Thomson. And J.J. Thomson, after reviewing ideas first put forward by Thomson Lord Kelvin, had this idea of examining what atoms could be made up of in terms of positive and negative electrical charges. J.J. Thomson's, ultimately his first greatest idea was when he was experimenting with gases or should I say, not gases, but tubes that were very, very low in pressure, so they had a lot of that gas removed. He'd pass high voltage electrical charges through them. You might think that we're talking about sparks, lightning, that kind of stuff. No. Just basically applying a very large differential voltage between two parts of this long evacuated gas tube. And if you measure the voltage that's applied, you can effectively determine what's going on the inside. And so he thinks that if he applies the negative to one end of this evacuated gas tube, you've got two plates inside of it, and both connected to a voltage supply. We'll apply the negative here and the positive here. He found that there was a flow of electricity in this direction because they came from the negative. That's the cathode, and were attracted to the positive. That's the anode. He called this discharge of electricity cathode rays. Apparently, there's something to do with a pinwheel on the inside at some point, but I think that was actually something to do with Millikan, but I know Millikan actually used the latex droplets. But effectively what we find out is this. He puts this little paddle wheel on the inside of, this glass tube, and all this is like hand-blown glass tubes, right? And what happens is when he puts it in the stream between the negative and the positive, the cathode rays, the electricity that's emanated from this negative electrical terminal, actually turns the paddle wheel around. And the only thing that can do that is something with momentum, right? And the only thing that can have momentum is a particle, because momentum is about mass and velocity, mass and velocity. So we've got these cathode rays, which are really just electricity, but apparently they've got mass. And this is where we generate this idea that these negatively charged, right, because they're being attracted to the positive, opposites attract, these negatively charged bits aren't just rays of electricity, but they are in fact tiny, tiny bits of matter. And so he goes on to do further experimentation, and again this was perfected later on by another physicist called Millikan. And what we determine is a mass to charge ratio, and ultimately a mass of an electron. And it is so small, it's almost insignificant, which is why it's so very, very difficult to detect. I think memory serves, it's about 1/1800th the mass of a hydrogen atom is the actual mass of individual cathode ray particles, which we come to know as electrons today. Tiny. So if that's 1/1800th the mass of a hydrogen atom, where's the other 1,799? Right? because they've got to add up. And on top of that, hydrogen, just like all other substances, is neutrally charged. So if I've got a negative tiny mass, there must be a positive massive mass. And this is where Rutherford comes in. So, it's being conducted at the University of Manchester, which is a famously gloomy place in northern England, and very famous for, obviously, for its football team. But it actually turns out to be a hotbed of like really ingenious scientific discovery. In fact, you may know Professor Brian Cox. He actually is at the University of Manchester as well, as an eminent physicist in his own right. So Rutherford is working in the basement with Geiger and Muller. No. Geiger Molotov. Geiger and the other guy. Apologies. And what they do is they start experimenting to find out what the atom is really, how it's really structured. The whole idea here is we're not going to discover exactly what atoms are made up of. We've found these small negative electrical parts. What he's really saying is this: what is the arrangement of these positive and negative bits? What is, if we've got these tiny little bits of negative, where's the big positive? This leads us to something called the Plum pudding model. The Plum pudding model is effectively that whole idea. It's like a Christmas pudding, but we've got this big positive with tiny bits of negative stuck in it, like raisins in a plum pudding. That's one idea. There is another idea actually that was out there that was called the Saturnian model, and that was where the negative electrons spun around the positive center. Okay, so which is it? Okay, gold foil experiment. I don't know if it's necessarily true that it was actually gold foil. It probably was, and the reason for that is very, very chemistry. It's because gold is incredibly malleable. You can literally, under compression, compress it down to foils, tiny thin bits of metal that are so thin you can practically see through them. And that's just the compression, that's just called malleability. You can, with a hammer, you can make very, very fine, very thin foils, which we know that Rutherford was looking for, because he was looking to find out what kind of deflection would happen if he bombarded these atoms of gold. Remember, atom means indivisible, so he's not expecting that he's going to like smash these atoms apart. In fact, he believes the idea to be the idea of quote-unquote solid liquid gas, right? It doesn't even extend to the atomic or the subatomic level. What he's expecting is, if we have a large positive with tiny bits of negative on the inside, and he sends through some very, very highly energetic particles, that what he's going to see is the particular particles he's choosing are what's called alpha rays. At this time, they were pretty new, and they were like the most energetic thing in terms of particle physics, particle chemistry. They were found that they were a part of naturally occurring radioactive substances, and they collimated an alpha stream. And what that means is you get like a chunk of something that gives off lots of alpha radiation, like radium, something like that. You get a little bit of that, and then you encase it in lead. And then what you do is you put a tiny little hole in that lead casing, right? And you extend the lead a little bit more, and you get yourself an alpha gun. All that's going to happen is the alpha rays that are always coming off are absorbed by, but only the ones that are traveling in that straight direction can make it all the way down. A tiny hole, and then it's also got this collimator, is what it's called, right? We do know that the alpha rays are positively charged. Now, this is a little bit of classical physics here, but we get something called charge density. Or in other words, if the atom is really big and positive, the alpha particle, which we assume to be really, really small, will travel through the positive, not solid, right? But through the positive area of mass, I don't know, amorphous almost. I mean, I think, because no one had any idea, I don't know what they were quite expecting, whether it would be like positive jelly or something like that, or foam, I don't know. But because it's large, the large part of the atom, we're going to see a small interaction as we pass through. So we're going to go through and we're going to get small deflection angles. So what that's going to mean is, on the far side, the detector, it's called a scintillating detector, a small dot, right, of alpha particles passes through the atom and it'll become a diffuse sort of section right there. We're going to see this small, almost like when you unfocus a flashlight. What actually happens? Well, we don't see a large unfocused blur at the very end on the zinc sulfide scintillating detector. We don't see it at all. In fact, what we see is we see a dot, we see another dot. Right? We shoot through this quote-unquote gold foil. It probably was gold, and here's the reason why. Because what we want to do is we want to make sure we're only getting a single deflection, right? So we've got this thin layer of these bits of gold. Gold also is incredibly dense, which means it must have very big, heavy atoms that are closely compacted to each other. So the chances that my alpha particle is going to pass through one of these atoms is very, very high. I don't want another layer. Because I'll get deflections upon deflections, right? And what I'm looking to do is just pass through, get a single deflection, and it sort of just blur at the very end. But this is not what happens. What actually happens is the alpha particles go through. They just go through. Well, it's a tiny dot of positive alpha particles. It's a tiny dot of positive alpha particles. Okay, so what does that mean? Well, it means that the alpha particles aren't interacting with anything. Nothing. Not air, nothing. I mean, they're going straight through. Like there's nothing there. So Rutherford's conclusion is that atoms are mostly nothing. There's nothing to them. But how then can they be so big? Well, Geiger and his colleague continue looking for possible deflection. So instead of this narrow pattern of weakly deflected, they start looking at different angles all around the gold foil. And what they discover is the alpha particles go in all right, and most of them keep going straight through. But some of them bounce off at crazy angles. Some of them even go back down the beam. Positive, we're looking for a positive. How can this possibly be? How can it be that most of them, like I think it's like 99.9% of all of the alpha particles that are emitted go straight through, but 0.1% get scattered in these incredible directions that quite literally Rutherford said was like seeing 15-inch naval artillery shells bouncing off tissue paper. Well, what are they bouncing off of? What could be there? Well, it has to be, instead of a very large positive, it has to be an incredibly condensed positive. It's that volume piece. And that means that instead of these alpha particles going straight through, they must come across something that is really, really small. This really tiny positive piece. The smaller it gets, the more intense that positive. So that the alpha particle goes by, or just collides with, glances with, and then bounces off and ends up in these bizarre scattering pieces. But that must mean that all the mass must be condensed in an atom, or the vast majority, into the tiniest fraction of an atom. And that's the truth. The mass of you, me, everything around us is actually condensed mostly in what Rutherford begins to call the nucleus, the center. But then how is an atom so big? Well, because it's got fluffy electrons on the outside. So it's a combination, right? That the nucleus is incredibly dense and closely packed together, and the rest of the atom is just absolute nothingness. In fact, today we have some terms for it. We call it a quantum vacuum. But that means that atoms themselves and everything around us and the whole universe is mostly nothing in terms of volume. Like, how do we have the appearance of being here? And the answer is the way that light interacts with it. But the truth is, if we could condense atoms down so that the electrons on the outside were, in fact, to collide or to get close to that nucleus, our volumes would shrink by over 99.9%. And if we take into account then all the spaces between all of the atoms, like in chemical bonds and then not bonded, most of what we are, it could be balanced on the head of a pin. It'd still weigh the same. But that's actually what your volume truly is. Another way of thinking about it classically is that this tiny little central piece of positive charge, the nucleus, that weighs everything, it weighs, 1,799 1,800ths, right? That tiny little bit would be like a pea at the center of a stadium, a sports stadium, with all of the mass of that stadium, and the electrons would just be a ghostly figment orbiting around in the outer stands. Thanks very much. Please like and subscribe.